wait and one's what we call signal. Um, some people did other creative things. In particular, some people had solutions. So the solution I sort of thought was the obvious one. It was not the only one, and it was possible to not introduce an additional semaphore if you instead turned the read count variable into, you used it like a semaphore, and you also looked at its value. So you use signal and wait, and you also test the value. Now, I didn't say not to do that, and so that's okay. I didn't, what made it so that the solution was different from what the TAs expected. That's why they all came back in regrades. So that's all right. But, so in future, if I really want you to use semaphores as semaphores only, I will remember to say use only signal and wait, not look at the implementation, but actually, in some ways, I have to admit, it's more elegant not to introduce another variable, since you have one right there in semaphore, and it does show that you understand how semaphores are implemented, although that wasn't even really the point. So, that's fine. However, there were some people who, rather than use a semaphore, essentially tried to implement a semaphore. Okay, you used a variable, an integer variable, and did it this way. Okay, or something. It's indicated some kind of blocking and unblocking. Didn't use signal and wait, which is what we have as tools to do that, and then sometimes did it wrong. Okay, that's more complicated. You're actually implementing the semaphore sort of directly in the code, and it's hard, it's hard to do that right, particularly when you've got a read-write lock going on. So, however, even though it said you may use a semaphore, I didn't require you to use a semaphore. I tried to give as many points as I could to people who gave this solution, but I really would like you to know what semaphores are and how to use them. Kind of the point, even though that is in some ways simpler, makes the solution simpler, and by trying to use test and set and busy waiting, shows, you read that part of the book on synchronization and paid attention during class, but still, I would like you, so in the final, if I say semaphore, I mean semaphore. Okay, didn't do it on this test, but you should learn semaphores well enough that you can use signal and wait properly. It will actually make your solution simpler, I think, and not try to work around it. Okay, so that's but I didn't break that way. We're going to hand you back papers here at the end. Okay, so any other general questions? Here, okay, so now we're going into paging more, and so paging is really mainly what is meant by virtual memory these days. Segmentation is still sometimes used, but only in conjunction with paging, and sort of hybrid architecture, not used by itself in any full-blown architecture that I know today. So we have the go back a little bit of this picture. Yeah, so this is our canonical page table picture, right? And just to remind you what's going on here, we've got a logical address or virtual address, same, you call it either, it's the same meaning. We've got a page number in the logical address and an offset, or displacement D. We're going to translate the page number to a frame number in physical memory, and that's through this indirection table. Just take the offset is without change, and that will give us a byte address in physical memory. And the other thing just to remember is we have these additional bits that can be in the page table to help us, as we'll see in a bit, with the algorithms for implementing different services. So we have just this ability to rearrange, push things together, or pull them apart and leave holes. The ability to leave holes in the virtual address space is very important. That's how we get the stacks way up at the top, and the code and data way down the bottom, and all this empty space in between. Empty space is empty space in the page table, entries that are what? Invalid. So this is just a more detailed example of that. And we have this problem then of keeping track of free frames in physical memory in order to be able to populate, say, a new process that's being created with pages. So we need to have a free list and be able to put them together. So what are the actual, the implementation of the page table, right? So again, perhaps after going through this grading and talking to people, really important in this course, I'm afraid there's no way around it, particularly in this part of the course. And this is a course about implementation of operating systems, mainly, not about their characteristics or how to use them. 360 is about how to use them. We talk a little bit about characteristics here, but I really like the idea that you all come out of this class knowing something about how to implement. So if you see the word implement, it means this. What is the mechanism? Okay? So if you see how is virtual memory implemented? How is the page table implemented? And you said the page table is used in doing the translation. No. That's interesting. It's not how it's implemented. Right? What I mean is the data structure you just saw a picture of, these details and the algorithms maybe that we use, those are the implementation. If you're someone who doesn't, really just doesn't like implementation, technical stuff, you tend to try to avoid it. So if you're asked a question about it, even very directly, you're going to give me characteristics. And just this is the time to get over that. Okay, between now and the final exam. Okay, and if you need to come talk about it in the office, I'm happy to talk with you about it and explain more in detail. But it just, I just kind of think it's really, when you ask one thing, what is the implementation? And you start writing about something else, it's just not going to go well. Okay, so in terms of studying for this course, every single major mechanism that we've talked about, ask yourself, do I have an idea of how it's implemented? No. The way I put it to one person I was talking to, like the idea, even though, of course, you can't write an operating system, it's too technical, but But I would like the idea that if you were stranded on a desert island, the only way you could get off was to actually write and operate the system. You would at least have some idea how to try. Okay, what the pieces are, what the you know, and if it's just no, what we can do is talk about high level generalities. I'm not going to get you up yet. So that's the one I want to get. The island is getting through this course with a grade that we need. So really, that's can't stress that enough. Okay, so we keep the page table in memory, and so you've got the base and the length, and then you've got the associative, we do the lookup as we've just shown, looking in that table with the page number, getting the frame number, and then we use this translation look-aside buffer that we talked a little bit about as a cache. Right, so that's associative memory, very important. Again, these, I have to say, the way these pictures are drawn, one of the reasons I like to use these pre-made slides so much is because the pictures, my pictures I'm going to draw on the board are much worse. But I will admit, it's a little, it's a little, could be a little unclear here. We've got all these blue boxes and gray boxes, and they're really quite different things. So it's worth being clear in your mind what these different bit boxes are, right? The CPU up there is, that's a processor, so it's mainly Boolean circuitry with some registers. And then we got this logical address coming out that's really just a value. Right? It's on the wires somewhere. It's coming out of the CPU, out of the read or write instruction. Okay. Then we have these three, and translated here to this other one, which is a gray box. We have this blue box, which is physical memory. Okay. So that hopefully we have a sense of what that is. This blue box is the page table, which actually lives in physical memory, but is shown here as a separate thing because it's functionally being used in a separate way. So we're looking things up in the page table, which is in memory, to get the address of the data item in physical memory. Okay, so both of these blue boxes are memory. Actually, this one's inside that one. That TLB is also a blue box, but it is a cache. It's memory inside the MMU. Could say it's inside the CPU, depending on if it's a single chip processor. The MMU is inside. Sometimes the MMU is another piece of hardware. But it really is separate from the memory. Okay, so this is a flow chart that shows what the flow is, but actually it's kind of a core key to physically how everything is implemented. And why does it matter? This is slow memory. The CPU is fast, takes about a cycle to execute an instruction. Physical memory is slow, about 10 cycles, 10 CPU cycles. Page table is slow because it's inside the memory. Yes?
Is the content of the page table itself subject to cache and randomity?
No.
It's not. So it's not. If the CPU doesn't ever check, it's on one caches.
The page table is the kernel is gonna exclude it from caching. Controls over the cache.
Why?
Why? Well, you don't want problems with consistency. All right. I mean, it may be that you could allow it cacheable, but you really want to make sure that you don't have inconsistencies in any kind if it's updated.
Okay, that makes sense. And if it's updated, do you want to
The kernel.
Okay.
So but that associative, the point is that TLB is an associative memory, right? So it's really like a whole bunch of registers. It's fast, operates, during a single cycle. And, so it's a different, in all of this, we really have three physical pieces: the memory, the TLB, and the CPU. And everything there resides in one of them. Like I said, just to make it more complicated, in modern CPUs, the MMU is actually part of the same chip. We went through a little bit about effective access time, and now we got into protection. So we have this valid and invalid bit, and so that allows us to generate an invalid bit. Not only allows us to show where there is no physical memory map, but allows us to generate a trap to the kernel if any access to that particular page is affected. So even if there is a frame in memory, we might want to rule out access to that page, as I said, because for some other reason. We have the option of doing that. So I gave you the example, which I hope is intuitive, of filling the area with virtual zeros, right? The kernel, rather than actually allocating space and writing zeros, just on demand, does that on demand and allocates memory, whatever a page, that invalidates all the pages, and if one of those pages is read, it allocates memory and fills it with zeros, so the zeros can be read. Actually, if you have virtual zeros, what do you do about a write to the virtual zeros? You kind of have a choice. You might say, if you have a write into the virtual zero area, you allocate the page and fill it with zeros, let the write happen, and then you just leave it there. Now it's a physical, a real page, not a virtual page. Okay, that kind of seems straightforward. But what if your virtual zeros are so big that you don't want to allocate pages permanently? And you want to say, I want to be able to unallocate them and use those pages in a different way. In that case, you might want to say no write to the virtual zeros. So if you get you an area of virtual zeros, you can, no writing. It's actually less useful when you think about it that way, but sometimes it might be you want to be able to read things. In which case, then you could use perhaps valid, invalid, maybe you have, as in segmentation, a write read-only bit. So it's starting to give us some tools to do some things here. So what else might we do? So sharing is one of those things. We talked about shared memory. We've talked about it on and on the whole semester. We have sharing of the entire address space between threads that are sharing, that are part of the same process. You have maybe the whole. Well, let's actually start even simpler. Before you share the code segment because it's read-only, so there's no reason not to share it. So you can share the code segment on a fork. On a thread creation, we share the code segment and the data segment and the heap, but not the stack. Because, why don't we share the stack?
Because different threads have different program counters, and the different and also need people to put temporary variables in different places. So they need to have different stacks. And that doesn't necessarily mean the stack is not separately kernel in each. It could memory is not. That doesn't mean that it's necessarily mapped differently. It just means the stack is different stack.
That's certainly true. We do different, but I'm saying when we do a thread creation at kernel level, we do in fact create different, we do map them separately, and the reason reason for that? Sorry? Protection in case of what? Overriding. Because of what event? Oh, no. Good try. No. um, yes, how many of you, in your programmers, does the word Stack Overflow mean anything? Okay, when you hear stack and you hear a problem might occur, and you might want your own segment, I don't know. So, that stack overflow is the problem, over allocation, but of a particular kind, namely the data, you have a data structure that grows and it grows into what's next to it. Very, very important. So you can't forget what you learned in basic programming. That's all important stuff and data structures. Okay, so we have sharing that the kernel implements for us. We haven't talked about how. And I even indicated we could have sharing between separate processes of, say, another area of memory, not one of the standard areas of memory that is really set aside just for sharing. So here's where we find out how they do that. So shared code we know about. With private code and data, that's kind of the standard picture on a port. But the point is, if you have an area, if you have some frames you'd like to share between two different address spaces, you can do that by putting pointers to those frames into two different page tables. Okay, two different page tables, or in this case, three different page tables. Okay, you can have here some of these pages, but not all of them. 3, 4, and 6 are shared among three different page tables, and therefore mapped into all three of these virtual address spaces. In this case, we see them being mapped in the same place in the virtual address space, but that's not even necessary. It's up to the operating system. You could put them in different places, right? This is what we say, when we have indirection, it's a very powerful mechanism, and you can do all kinds of things. It's easiest to manage this if you have frames in the same place, so that pointers to them can be passed back and forth between these processes. If you have that, your operating system will tell you, we're going to guarantee that, but that means you can only create shared memory then if you have space available in all three of these address spaces in the same place. So depending on how you're going to use it, you can go in different ways. You could, why might you have things mapped into different places? If it's an operating system that gives you very dynamic paging, the sharing of memory, creates them, deletes them, then it might be easier just to find some free space in the virtual address space and map the frames in wherever the first place is found.
So if you've got a shared frame or something like that, when you declare it, you have to declare it as, hey, I'm declaring this as a shared piece.
Good question. So that is a good point. So we have this mechanism for doing weird stuff to memory, like sharing it with another process that can read it or maybe change it. Okay, and what does that do to the programming model? Okay, of the processes that are sharing it. So the first question is, what is the programming model? The programming model is now, there are areas in memory that are shared and that can be changed by other processes that share them. How do you deal with that in a high-level language? Well, first question is, how do you deal with it in C? And in C, there is no way of declaring shared. So what you do is you just have an area of memory that behaves strangely. And the programmer has to know it and has to deal with it. So that's C. You might say, but the compiler, if the compiler doesn't know it, compiler might do some things like put the values into registers, and then they will change underneath in the memory because the other process changes them. And so maybe if you don't tell the C compiler, it's going to produce code that won't run correctly. And that's true. That's true for shared memory. It's true actually for memory that's used in I/O, another form of sharing. So C does not have a keyword that says this is shared. It has a keyword that says don't put these values in registers. And so if you're using this, you have to do something like that in C. Okay? If you don't, then the compiler might misbehave in terms of that. So what you're doing at that point is really using C at a very low level. You're using it and you're using it with knowledge of the operating system and the architecture, really, and taking care of things that have to be taken care of to make sure that work. And how about in a real high level language? Java, right? Even any Java is a good example, similar to C. In a real high level language, the the programmer would not have direct access to shared memory. Okay, because of this kind of reason. Just like in Java, you don't have direct access to the underlying threads. Okay, you have Java threads and the Java virtual machine. If there's a thread mechanism in the operating system, it'll use that to implement that. So in order to use this in a high-level language, you have to reflect this functionality into the language, and then the language is going to use the operating system to implement it correctly. So it's only operating system writers, C programmers, and other low-level types that actually deal with these mechanisms, and compiler writers for higher-level languages. And this is why I mentioned it before. People who work with these mechanisms to do research, they publish, one of the main places they publish their papers is in a conference called Architectural Support for Operating Systems and Programming Languages. Because it's really more advanced kinds of things, you really need the operating system working together with the programming language to make it available to the programmer. That one. So definitely, unfortunately, even if you take a compiler's course, you're not going to learn this is kind of advanced compiler stuff. Or the languages course teaches how to use a language, maybe, that you need to do. How you implement them, that's quite specialized stuff. How you use operating systems, advanced features, implement language advanced features. Kind of specialized. Okay, so as you might, if you did any calculation in your head, which I haven't did, but you thought about it a bit, you might realize that those page tables for a modern operating system gets really big, really big. Even though your page size might be, say, 4K, originally page size is like half a K. Say it's 4K, which is not at all big these days. Then a 32-bit address space, if you wanted to fill it up completely, would have 1 million entries, right? So it would be several meg of memory just for the page table for each process that's that size, right? And remember, the way we described it, if you have a page table base and a page table length, but if you use the high memory and low memory, maybe just one page in each one, even if the rest was all invalid, you would need all of those invalid entries in between. If you don't have any way of compressing the page table itself, it needs every entry for something between its base and its length has to be populated with something, even if it's just an invalid entry. So that would be big. That would be much bigger than the TCV. Okay. You would like to avoid putting that much memory, much of it perhaps wasted, in describing empty space in between the stack and the heap, and the data segment. So we want to do other data. What we do is we build other data structures that have the same functionality or similar functionality. That is, as a function, they're going to be the same as a page table, but their performance characteristics are going to be different, and their use of memory is going to be different. So we have different ways of doing that, and hierarchical paging is the most important one, and hash page tables is also pretty important. So we're going to cover those, and but again, I want to make it really clear, where are those data structures? Where are they implemented? Where is the logic to implement them?
Here, the code that we, well, not really the code, the logic to traverse the lookups is in the hardware. The logic to manipulate them, to make, to change them as needed is part of the kernel.
Right, so that those are the two places. They're created by the kernel and written by the kernel, read by hardware. Which hardware? Right, the NMU, memory management unit. So I just want to stress, when I start talking here about data structures and algorithms, I am talking about things we're implementing in hardware. We're changing now the hardware to be more sophisticated than a simple indirection into the page table. We're actually doing substantially more complicated work, and none of this work is, by the way, it's not going to be in firmware because it needs to be fast. So this stuff is actually, this is the reason that MNUs were for a long time additional chips outside the CPU because there just wasn't enough silicon on the CPU. Well, it's a substantially complicated function in MNU. So the first difference, and the one that you most that is most common to find, is hierarchical page tables. The idea is you want to be able to have page tables that are sparse, that are not dense. Right? Dense means from the base to the length, every page number has to have an entry. So that's a dense implementation. Sparse means we know that many of those are invalid, so we only want to implement the valid ones. And anything that's not implemented will be assumed to be invalid. Okay? So that's the difference between a dense implementation and a sparse implementation. And the simple way to do it, you have two levels. Right? So we have first level page tables, which look just like page tables we're used to, but they're limited size. And then we have, that's the outer page table, which is a table of tables. Points to those first level page tables there, or maybe you want to think of it right second level, the page tables closest to the memory that have at least one entry that is not invalid. Okay, so if you have a whole page table at this level which is invalid, you don't have to implement it, you just put an indication of that at this level. So now this is still a dense implementation, but it's much smaller. Okay. Another way to look at it is this is now a tree, right? Now a tree rather than a simple table. A simple table is a kind of degenerate form of a tree. So this is now a two-level tree. Because of that, it's capable of being very bushy and grow out to its full capacity, but if it's sparse, then it will be much smaller.
But, why do we have the two-level page table? Like, what is it, to solve? Because, tell me if I'm wrong, but from what I understand, on a single-level page table, if you have a miss in the TLB, and then your information is on disk, you can have a page fault while you're waiting on it to pull the memory from the disk.
Okay, so that's a very good question because here's the thing to wrap your head around. None of this yet has anything to do with this.
Okay.
It's just mapping virtual addresses to physical addresses. Okay? Now we are going to use this to implement something which is like swapping. Okay, but for so far, everything I'm talking about, if it's invalid, all it means is there's no frame there, or you're not being allowed to reach the frame. That's all invalid. Doesn't mean there's anything on disk. Could mean the operating system wants to put zeros there. It's just this very generic mechanism.
At this point, a miss is just like it can handle a miss gracefully. Is that what it's
Right. You can handle a miss by going through memory. The reason we're doing this is to save memory. That's the whole reason we're doing this. We want a small process, a sparse process, not got all its pages crammed together to take up less space, not to be the maximum space. Right? And again, you could say, oh, if you only have 5 frames, you only have 5 pages and therefore 5 frames, why not put them all at the bottom and have it be dense? That's not the way operating systems want to use the virtual address space. They want to use the entire virtual address space, stack at the top, coded data at the bottom, keep in the middle, and still have room left over for shared memory segments they've allocated in the middle, or mapping files somewhere else in the middle. All of these kinds of things are tools of the operating system. So we need that whole canvas of 32 or 64-bit virtual address space, even 128, although that didn't take, but we did have it for a while. 128-bit virtual address space is kind of like the 12-cylinder car. You do it, tried it, and it didn't really get them that much. So, but that's what we're getting out of this. So how do we actually? You said I think the other right word that you have to just bear in mind about this. This is making misses more expensive. Right? Obviously, we just added another read to what happens on a miss. So we did a miss 50% more expensive than it was, okay, in all our little calculations. And the reason any of this works is, right? Yeah. Specifically, not just any cache will do. Which cache? It's got a name. The TLB, and it's 99+% hit rate. Okay, that is what is making this work. Even though we talk about this mechanism as if it could happen on every single read or write, the truth is you get a few misses, the TLB is full, you get no misses, almost no misses after that until your use of virtual addresses changes. You subroutine call or something. Address being accessing data structure. But really, it's a very, in some ways it is I don't know, it depends on who's in the field. I think you could just as rather elegant that we actually implement it. We have a virtual address with two page numbers. A first level page number and second level page number. Okay? And together those specify the page. Okay? And then we have an offset. And so we're going to use P1 to index into the outer page table, and then when we pull up the inner page table, we use P2. Okay. What are the sizes of P1 and P2? Well, they're determined by the layout of the virtual address, which is generally fixed and determined by the MMU. So this is in hardware. Okay. You could have some flexibility, but remember, we want this to be as fast as possible. So we tend to take away the flexibility in return for speed. Now, what is the picture that goes along with that? We only show you part of the picture. All right, this is the outer page table that points to the inner page table, right, P1 and P2 are those offsets. You know, literally, wires coming from the virtual address register that's coming out of the CPU and going as offsets into, so they're added to the base of these tables in order to index into them. And that gets you then, when you see at the end, you get the offset, you get the bypass. Okay, so that's the picture. Three reads, or two reads to do a read or a write, is that way? On a miss. And think about this, you might say, well, gee, we have a 32-bit address space, we have 4K pages, that is, you can't have tables in the back page. But in a 64-bit address space, you got a lot more room to work with. Okay? And so we have perhaps a different allocation of pages in which you have 42 bits of outer page table. Quite a bit. Means the outer page table has a large maximum size. You don't have to use the whole thing. But the inner pages are still relatively small. So you now have 1K pieces inside tables, so 1K pages, or 1K frames, I'm sorry, we'll call it 1K entries in those inner page tables, 1,000. So that's another way, and as you can see, that 42 bits is quite a large canvas on which the operating system can implement its services. A lot of space to work with there. This is also the reason, though, why people talk about 32-bit address spaces. Actually, I remember when they became common, when they became a thing in the early 80s. People said, oh, this is it. This is all we'll ever need, because who's going to want to address more than 4 billion things? First of all, address 4 billion, okay, not that many. But also, you don't want to use the whole address space in a dense way. Address 4 billion. You want 4 billion addresses to put however many things you want to put in there. It could be far fewer than that, but if you have a big address space, you can do all kinds of creative things in how you lay them out. And so 64 bits came along, and you said, oh, well, that's more particles than are in the universe or something, and it just doesn't matter, because address space is a resource. If you have more of it, you can use it in a more profligate way and write algorithms that are more efficient or more convenient code or whatever it is. Not necessarily even using that much memory, but using that much address space. So that's the thing to bear in mind. Went as far as 64, and as I said, 128. It turned out the costs were greater than the benefits. You're counting differently than I am. Memory access, I say 4, I said 3. Figure out what it is. But it's a lot. It's a lot. On this, you get a lot of memory access. Okay, so that's the basic tools we have here. What we want to do now is talk about, first of all, that's one approach. The other approach we're going to focus on here is what's called the hash version. Use much less table about. We're going to talk about a few services that use that table, however it's implemented, to implement some more services. Okay, with that thing. Oh, that's a blank. Come up if you want papers back